In this recording, we're going to learn how to graph and confirm the behavior of rational functions that have slant asymptotes. In other words, we're talking about where the degree of the numerator is greater than the degree of the denominator. Okay, so let's write about that a little bit. Okay, so what do we have here? Well, this right here is the function that will be the slant asymptote. Keeping in mind, this could be a non-horizontal line. It could be another function like a parabola. Okay, and p of x is our numerator. Q of x is the quotient, and that ends up being the slant asymptote. The quotient when we divide p of x by h of x. Okay. So p of x, the numerator, is what you get when you multiply the quotient times the denominator, the divisor, plus the remainder. Okay. So we're going to, in other words, need to do some division in order to find out how that slant asymptote is going to come out. Let's apply that to a specific example. So we're going to graph this rational function where the degree of the numerator is greater than the degree of the denominator, and then we're going to confirm its behavior. And when we confirm its behavior, remember there's 5 pieces. We're going to find the asymptotes. Those could be horizontal or vertical. I want to find the x and y intercepts, and then what's the intermediate behavior near our asymptotes, our vertical asymptotes. Okay. So first off, we want to find the end behavior asymptote, that slant asymptote. Okay, we're going to find that end behavior asymptote. And how do we do that? Well, we have to find the quotient. We have to divide these two polynomials. And we do that either using long division or synthetic division to find q of x. Okay, so let's do that. Let's work that out. Haven't done that in a while. Okay, so it's the numerator divided by the denominator. Now this is a special situation where I have to be careful in my numerator. There's no x term. So I have to make sure I leave a 0x, a placeholder. Okay, so you really got to concentrate, obviously, with polynomial long division. There's a lot of little places where you could go astray. Minus sign or something. So the process we're going to use here is we're going to look how many times does this leading term go into this leading term, and continually do that with what's left until we're finished. So in the first situation, 2x cubed divided by an x squared is a 2x. So now I need to distribute that 2x to all the terms in the divisor. Distribute 2x times 2x squared. 2x times x squared, so 2x cubed. Then distribute 2x times 2x, etc. And 2x times negative 3. Okay, you want to be really careful here. I'm going to be subtracting this entire bottom polynomial. Subtracting the entire thing. I make a lot less mistakes with addition, so I'm going to change it to addition of opposites. I'm going to change all these signs to be their opposite. Now I can just add. Those add to 0. Those add to 3x squared. Those add to 6x. At which point we bring down the minus 4. Now I'm going to move the highlighter here right to there. I'm asking myself, how many times does x squared go into 3x squared? Of course, that's 3. Now distribute the 3 to all the terms. 3x squared, 3 times 2x, 6x, 3 times negative 3, negative 9. Okay, again, subtract the entire expression. I encourage you to write it as addition of opposites. Changes that negative 9 to be a plus 9. Adds to 0, adds to 0, adds to 5. So we have that 5 as a remainder. And we have this 2x minus 3 as our quotient, called q of x. All right, that was fairly laborious here, okay? But that's what the slant asymptote is. We just found out that y equals 2x plus 3 is the slant asymptote. That's our end behavior asymptote. And the cool thing is, when we look at the graph, it will be confirmed. That's the nice thing about this relationship between the algebraic process and the graphical answer, is that we're going to confirm everything. And if something's amiss, we're either going to see it in the graph or we're going to see it in the algebra. Okay. The rest of the steps are pretty straightforward. You're going to find your vertical asymptotes. Okay, hopefully you remember how to find those vertical asymptotes. If so, go ahead and do it. Play the recording when you're ready. Okay, hopefully you got that. Kind of go through that fast here. Okay, so those should remain our vertical asymptotes. We'll check that graphically and on the table. Okay, so we got 2 sets of asymptotes. We want to get 2 sets of intercepts next. You can do them in either order. We can do the x-intercepts. But these aren't going to be quite so easy, setting that numerator equal to 0. What we can do is we can get them graphically from our calculator. So let's check that out. Let's go ahead and put in to the graphing calculator that function. All right, now that that's in there, we can look at a graph. So let's start out with a zoom 6, just to get a sense of where the graph is. Okay, I think we can tighten it up a little bit in the horizontal direction. So let's do that. Maybe just negative 5 to 5. Let's see what that does for us. Okay, that gives us a pretty good sense of the graph there. All right, now I want to find these x-intercepts. So we can find that. Those are the zeros of the curve. So I can do a second trace, and I want to find choice 2, the zeros. I'm going to have to do this repeatedly. I have, looks like 1, 2, 3 separate zeros. So left bound, I'm going to pick a number over here to the left of the one I'm trying to find. So that should be negative 4. So I can just type negative 4. Okay, so it puts a left bound there for me. Right bound, I could say negative 3 if I like. I can also move the cursor. And then guess, well, anywhere close, say negative 3.5. All right, it turned out to be negative 3.31. Oh, 3.32. I'm a terrible rounder. Gosh, look carefully at it. All right, so I'm going to repeat that process. This one looks like it's right around negative 1. I'm going to show you a different way to do it this time. So we'll go second calc 0, but this time I'll move my cursor to the left of that point. Okay, so it should start coming up here. Anywhere close in here will work. Right bound to the right of it, and then a guess will work. Okay, so negative 0.87. Okay, and that's what I had in my notes. That's good. And finally, this point over here. So if you haven't done this on your own, you have a graphing calculator, do it. If you're working with Desmos, you can just click on it and it will show you what the x-intercepts are. Okay, and then 0.69. So we have our 3 x-intercepts that we found graphically. Let's make a sketch of this. We'll do a screenshot and we'll put it into our notes. So I'm just going to put it here temporarily because you can't do a screenshot, so I won't do a screenshot in the notes. So let's sketch this out. Okay, so we've laid out ourselves a scale here, and we're going to try our best to plot some points. So we had the x-intercepts that came from our graph. And so again, the tool we used was second, calc, and then 0. Okay, and then we had our, we can get rid of this thing here. Okay, I was imprecise here. Let's go back and fix our vertical asymptote. Hopefully you caught that. Hopefully you're catching my mistakes. I do appreciate that. If you're screaming at me through your computer screen or your phone, it needed to be in a negative vertical asymptote. Again, this is the confirmation process. I would have caught that when I looked at my graph, which I just did, right? I realized, hey, that doesn't make sense. Got our asymptotes in there. Let's sketch out a graph. Oh, I got to put in my slant asymptote as well. So we got this y-intercept of 3 coming from this 2x plus 3. We're going to go down to right 1, so right about there. So we should have a slant asymptote that does something like this. There. Okay. And so that's pretty much what the curve is hugging. Curve comes up along here and hugs that vertical asymptote, and it extends along the slant asymptote like that. The other portion of the curve comes up along the slant asymptote, hits that x-intercept, makes a U-turn, and comes down along that vertical asymptote. And finally, we have a little portion of it that's up here that follows the slant asymptote and the vertical asymptote. So kind of a complex graph, but once we have that all in place, we can kind of see its shape pretty well. And again, I'll label the slant asymptote. Got the vertical asymptotes labeled. We've dotted each of our x-intercepts, and we have our function. So we just need to state what the y-intercept is. Again, we can find that out by subbing in a 0 for all the x's. Let's just do that mental math here. That's a 0, that's a 0, that's a 0, that's a 0. I'm left with a 4 over 3, right? So hopefully that part makes sense to you. Okay, so let's box some stuff in. We've got x-intercepts. Try to box in our final parts here. And y-intercept that we found by subbing in 0 for x. And finally, our intermediate behavior. I can put that over here. So, what's happening to the left and the right of each of those two vertical asymptotes? See if you can figure this out, and then play the recording when you're ready. Okay, so if you didn't yet pause the recording and work these out, please do that. If you did, these were the answers you probably got. Coming to this asymptote from the left of -3, we're going up towards positive infinity. To the right of -3, as it approaches -3 from the right, we're going towards negative infinity. as we approach x equals 1 from the left side, we're going towards negative infinity, and vice versa on the positive side of 1. Thanks for watching.